Have you ever actually stared at your screen and thought about what's really happening behind the glass? We casually click a mouse or tap an app, and instantly, all these complex actions just happen. But if you think about it, a computer at its core is literally just a collection of metal, plastic, and silicon. Honestly, it's basically an expensive paperweight until we add the real magic ingredient, software. So welcome to this explainer. Today we're going to unpack the invisible, almost miraculous hierarchy of code that actually makes our devices function. Let's dive right in and discover how we get from cold, lifeless silicon to the vibrant, interactive screens we rely on every single day. So here's our roadmap. We'll kick things off by looking at the two fundamental types of software. Meet the ultimate manager, the OS, and see how it handles system interrupts. After that, we'll dive into high versus low-level languages, how we actually translate that code, and finally, we'll take a peek inside the developer's toolkit.
All right, let's start with Section 1, the foundation, the two types of software.
Okay, so right off the bat, there is a very clean, absolute separation between what the computer needs and what we humans need. On one side, you have system software. This is the collection of programs the computer strictly requires just to function. You can kind of think of it like the autonomic nervous system of your device. It's quietly managing the heartbeat and breathing in the background so the machine doesn't just crash. On the other side, we have application software, or what we usually just call apps. This is the stuff you need: your web browsers, your games, your word processors. Application software is totally optional for the computer's basic survival, but obviously it's absolutely essential for actually getting our daily tasks done.
But here's the catch. Before that main system software can even clock in for work, the computer literally has to wake up. And that's where firmware comes in. Firmware is system software that's embedded directly into the physical hardware devices themselves, usually on read-only memory, or ROM. A perfect example of this is the BIOS, the basic input-output system. When you hit that power button, the BIOS's one and only job is to kickstart the hardware components. It's like the computer's first cup of coffee, getting the hardware ready so the rest of the software stack can actually load. It quietly does this crucial job every single time you power on.
So, once the BIOS successfully wakes everything up, it hands the reins over. That brings us to Section 2, Middle Management, the operating system.
The operating system, and we're talking Windows, macOS, Linux, whatever you use, sits perfectly in the middle of this whole shebang. As you can see, it acts as the absolutely crucial bridge between the cold physical hardware and the high-level application software. Without it, your favorite video game literally wouldn't know how to talk to your physical mouse. The OS provides a clean, user-friendly interface that lets you, your apps, and the hardware all communicate seamlessly.
And let me tell you, the operating system is incredibly busy. It is the ultimate multitasker. It manages your peripherals, making sure that when you plug in a webcam or a printer, it just works. It manages your memory, carefully handing out resources so different programs don't accidentally step on each other's toes and overwrite data. It handles multitasking, which is why you can listen to Spotify, download a massive file, and type a document all at the exact same time. It also manages drivers, those little utility programs that give highly specific instructions to devices. And of course, it manages your file system, keeping track of where every single photo and document is saved on your hard drive. It is a monumental juggling act, happening constantly.
So, to recap this boot sequence, it builds upon itself in a very strict order. Step 1. The firmware activates the hardware. Step 2. The operating system loads up on top of that firmware foundation. And finally, Step 3. Your applications run on top of the operating system. It's like building a house. If any single layer is missing or broken, the whole sequence just collapses.
But what exactly happens when our super busy OS manager gets an urgent tap on the shoulder? Let's look at Section 3, Handling Emergencies, or System Interrupts.
An interrupt is, well, exactly what it sounds like. It's a signal sent to the OS that demands a temporary pause in whatever program is currently running. When this signal fires off, it's caught by something called an interrupt handler, which then triggers an interrupt service routine. The OS literally hits pause on its current job, assigns the new interrupt a place in a priority queue, figures out how important it is, and deals with it. And honestly, the craziest part about all this? A modern processor might handle thousands of these interrupts every single second, but it happens so incredibly fast that you and I never even noticed the OS took a break to put out a fire.
Now, these interruptions basically come in two main flavors. First, you've got hardware interrupts. These are physical triggers, like you tapping a key on your keyboard or moving your mouse. Your OS has to process that input instantly so your cursor actually moves on screen. On the flip side, we have software interrupts. These are panic signals sent from the applications themselves. A classic example, a math error, like a program trying to divide a number by 0.
It's impossible, right? So the application basically throws its hands up in the air, fires an interrupt to the OS, and the OS steps in to kill the process before it can crash the entire machine.
Okay, so up until now, we've talked a lot about how software runs. But how is it actually built in the first place? That brings us to Section 4, the creators, programming languages.
Pretty much every programmer out there has to navigate a grand trade-off. You see, a computer processor only really understands binary machine code, ones and zeros. That's a low-level language. Writing in low-level languages lets programmers build incredibly fast, highly efficient code that squeezes every ounce of performance out of specific hardware. But man, it is notoriously difficult and tedious for a human to write and debug. Conversely, high-level languages, think Python or Java, use standard English-like words. They're vastly easier for us humans to read, write, and fix, and the code can run on lots of different machines. The trade-off, though, because it has to be translated, it's slightly less efficient and runs just a bit slower.
Now, there is a pretty fascinating middle ground here called assembly language. It sits right above that raw binary machine code. Instead of forcing a developer to type out endless mind-numbing strings of ones and zeros, assembly language uses these short little memory aids called mnemonics. So, for example, a programmer might type INP for input or RET for return. Make no mistake, it's still very much a complex, low-level language, but it gives the human brain at least a little bit of a foothold when trying to write super-fast, hardware-specific instructions.
But here's the thing. Your computer's processor doesn't actually understand high-level English words or even those assembly mnemonics. Section 5, the translators, compilers, and interpreters.
To make high-level code work, we have to translate it back down into machine code using special applications. And there are two main ways to do this: compilers and interpreters. A compiler takes your entire block of code, translates the whole thing in one giant swoop, and spits out a finished executable file. It's super fast when you finally run it, but it only tells you about your errors at the very end of the process. An interpreter, on the other hand, is more like a live translator. It translates and executes the code line by line. If it hits an error, bam, it stops immediately. That instant feedback makes interpreters incredibly popular for beginners and developers who are actively trying to hunt down bugs.
So, you might be wondering, where does a programmer actually sit down and write all this? Let's wrap up with Section 6, the workspace, the developer's toolkit.
Professional developers use an IDE, which stands for Integrated Development Environment. You can think of this as the ultimate high-tech workbench. Right in the middle is the code editor, which is packed with clever features to save time. It's got auto-completion for common phrases, auto-correction that automatically closes your brackets, and a lifesaver called Pretty Print, which color codes and indents the text so you don't go cross-eyed staring at a wall of code. But it's not just a fancy text editor. A good IDE actually has those translators, the compilers or interpreters, built right in. It features error diagnostics that will point to the exact line number where you made a typo. Plus, it gives you a safe, runtime environment to simulate and test your program before you release it out into the wild.
And really, that brings us full circle. From the very first jolt of the BIOS firmware waking up the machine, up through the frantic, non-stop management of the operating system, all the way to the shiny, high-level applications built in modern IDEs, it is an incredibly intricate, lightning-fast ballet. So the next time you casually click a mouse or swipe a touchscreen, take a second to ask yourself, how many invisible layers of code, on-the-fly translations, and microscopic interrupts did it just take to make that simple action happen? Honestly, the answer is astounding. Thanks so much for joining me on this explainer of the software stack. Keep learning, keep questioning, and I'll catch you in the next one.